All right. Hello, everyone. Welcome back. Hope we had a good weekend. Math 154, Week 8, Lecture 1. You know the drill. Going to talk about the whiteboard for a few minutes. Some important things to announce, as well as some important things that we've already discussed that we'll talk about again briefly before charging headfirst into Chapter 6 with 6.1. So my math lab homework's 5.1 through 5.4 due today and then on Thursday, the 13th and the 15th, and those are just coming in pairs. And then we'll finish 6.1 today, so that'll be due in a week on the 20th. The next Excel file, 5.1 lines, we talked about last time, so that's due on the 15th. We will do one from chapter 6 that'll be announced next time. And then there's one more that I want to do, but it's kind of pending time whether we're able to get to it or not. So we'll talk about that when I feel ready to. And then discussion board, week 8, lecture 1, that's today. So that's page 226. I had already announced it was going to be page 224, 226 last time. We decided to go 226. So that's announced today, which means it'll be due in a week. And we'll talk about the details of that in the class itself. We gave you a new video quiz last time, video quiz 2, that's going to be due on the 15th. And then I'm giving you a new video quiz 3 today that's due on the 20th. So both of these are in Canvas, both of them. There's a spot to download the file, and then there's a spot to upload the file, and I will have to hand grade these. So when you submit your quiz, don't expect a grade immediately. It might be 24, 48, 72 hours, and that would be after the actual due dates, not just from when you submit. I am going to go ahead and let you know there's going to be, and I've already mentioned that there would be one or two more past this, but there's going to be two more video quizzes, video quiz 4 and 5. I'm not saying the due dates yet. Obviously, they're going to be coming up really quickly, given a lot of details of the course. But I have gone ahead and made them available in Canvas. Somebody had asked me, hey, if you're just going to go ahead and do these video quizzes, could you go ahead and post them? And I figure it's about the end of the semester. If anyone wants to get ahead on a couple of things, that's fine. Versus the beginning of the semester where I really fight anyone trying to get ahead because we have so many different perspectives of this class to cover. It's just not a great idea. But we're at that point. If you're comfortable and you can knock out these video quizzes really quickly, then you can just go ahead and rock them. So yeah, they should all be available at this point, at least up to the fourth one. I might have made the fifth one available. I think I made the fifth one available. I've had a lot of things I've done in the past 48 hours, as I'm about to talk about in a little bit. So I think I made the fifth one available, and if not, you'll see it in the next day. So midterm, one of those dates is already passed. If this is news to you, that's kind of terrifying. Reminder that you should be watching all of our classes, yada, yada, yada. But Monday and Tuesday, 12th and 13th, Monday's already gone. Today's the 13th. 4 chapters with material, 20 questions, 2 hours in my math lab, 1 attempt. Make sure you submit your work in Canvas within 15 minutes. I did make that available super early yesterday morning, but you can take that up to any point until 11:59 p.m. tonight. That is when the submissions will shut out. Remember, there is a review in Canvas, and then there's also a formula sheet in Canvas. It's a very short conversion formula sheet. It's only 2 formulas, I believe. So you're not going to see any finance stuff in there or anything having to do with percents, et cetera, et cetera, et cetera. So we're going to start talking about next time. I want to say next time. The final exam is going to be on the 29th, just so you know. And you'll get the official write-up like I do with everything. I'm just giving you a taste, a preview. But the final exam is going to be on the 29th. So that's only like 2.5 weeks away. I just want you to go ahead and know that. So it will be in place of what would have been week 10, lecture 2. But for the final, it's 1 day only. I can't give it over 2 days. And because of that, we will not do a lecture in case anyone only has the availability during class. So week 10, lecture 1 will be the last lecture. Then that Thursday, the 29th, there will be no class. You just take your final exam in my math lab at any point in that 24-hour span up till 11:59 p.m. And then the course will be done. But the last thing I need to mention before we move on to the material today in chapter 6, where we talk about this exponential growth, which is such an amazing topic. You're going to hear me gush over it constantly and how it can just open up lots of math things in our world. Unfortunately, due to some circumstances that can't be avoided, you know what this means, I have had to, and I've already done this, I've had to pre-record next class as well as the class after that. So that is Thursday the 15th and Tuesday the 20th. So 7:15 and 7:20 classes are going straight to YouTube. Unfortunately, dire circumstances have come up. It is what it is, but I'm going to make sure that y'all won't have to miss a beat due to stuff going on with me. So I have already recorded these. I haven't uploaded them to YouTube. I've been doing 10 billion things, unfortunately. So once we finish classes today, I'm going to do those uploads. And if you wanted to get super ahead, you could. If you want to wait till the 15th and 20th to watch those classes, you can. It doesn't matter, but just remember that you are responsible for watching them by, the 22nd, when we will have the class after that. So everything will be back to normal on the 22nd. I apologize immensely. Per usual, I will be available through email. I just will not have the ability to broadcast these classes live. So I have scraped and scraped and scraped, just focusing on this to make sure that y'all don't miss a beat, to make sure we can finish the material. I'm sure people wouldn't have been mad missing a week of class, but that's just completely unacceptable to me. We got to keep things professional. So that's, again, the beauty of this. I don't have to get a substitute teacher or anything like that. It's all going to be available to you without missing a beat. So I know I'm repeating myself. I apologize for this kind of late announcement. But again, this shouldn't affect you at all. Yeah, so hopefully there's no questions or issues with that. If any of you try to go to class on the 15th or 20th through Zoom, you're just going to see that I don't ever start the class because, again, it's all been pre-recorded. I was unavailable to do it live. Apologies, but making the best of the situation. You will get the exact same material. You will get the exact same whiteboard announcements. You still have me available through email. I have gone ahead and set up, in fact, all of the future homeworks like 6.2, 8.1, 8.3, the next Excel assignment, the video quiz 4 at least, and I believe video quiz 5. So you pretty much know what you're responsible for the rest of the semester. Also, a friendly reminder that the project is going to be due on the 25th. I'm not going to talk about that every single class since we made that very, very, very clear a couple of weeks ago. But just one last reminder, well, not one last reminder. I'm going to remind you one more time before the 25th, obviously. You know me and reminders. But yeah, just a reminder that the project's due on the 25th. Remember, that's supposed to be independent. A couple of you have emailed me asking questions, and some of you are looking for more direct answers, which I'm not generally going to give. I'm more of a hint and push and nudge in the right direction for a project thing like that. And I'm not saying I can't help you. I'm just saying if you ask me, hey, what should I type in the cell? You're not going to get that answer from me. I'm going to say, well, hey, we think about this idea, think about this formula, think about what you have to do in this scenario, maybe giving you a parallel. Yeah. But per usual, I will be in the chat if you have any questions while we're doing this. So again, we're going to start with chapter 6. We're going to pick up with that. We're going to go into the idea of exponential growth. We're going to introduce some formulas, some concepts, talk about some guided activities, let you know what this discussion board will be on. And yeah, here we go.
Constant percent change. And there is another name for this, and its other name is exponential growth or decay. Now, I'm going to remind you what your growth factor and decay factor are. Growth factor is 1 plus r, where a decay factor is 1 minus r. That was something we did back in chapter 4. And then we had some new amount is an old amount times the growth factor or decay factor. So you could have the minus if it's decay. That's what I'm saying there. But we're going to mainly focus on growth in this course. We don't do too much with decay. Very, very, very few problems with decay, in fact. Just our teeth. Ha ha ha. So we have seen that by using a growth or decay factor, when something is changing by a percentage over a year, that we can find the new year's amount based on the old year's amount times its growth factor, where the R is the growth rate, the growth or decay rate. Again, these are all just reminders. Everything I've said so far is not new. So this is like, all right, you have a savings account that gains 5% interest annually. So if you put $10,000 in the account, you can find the interest by just taking the 10,000 times your 5%, or you can find the new amount by taking 10,000 times 1 plus 0.05, which is the 5% converted to a rate. But all of that was only true for one small interval of time, typically a year, a month, or day, or whatever, depending on the problem. The problem has to tell you if you're growing at an annual rate or a periodic rate of a month or a day or a quarter or anything like that. And we will see both of these types of problems. So what happens if you want to find a new amount after several iterations? Let's say you put $10,000 in a bank account and you leave it there for 50 years and you want to mathematically figure out, well, how much do I have at year 50? Well, everything that I've just said entirely relates to this new equals old times growth factor, but to find out how much you have at the end of year 50, you'd have to find what you have at year 49. And to find year 49, you got to do year 48. To do 47, you got to find 46. To do year 35, you got to do year 34. To do year 3, you got to do year 2. To do year 2, you got to do year 1. So if you want to find how much money you have in, just using this simple concept, it would take you 50 rows of work. Now, if you're doing it by hand, extremely time consuming. If you let Excel do the work, all you got to do is set up your formulas, drag and drop, fill, boom, you're done. But at the same time, it's still going to take up a lot more space. So this is called an iterative method, where to do year 50, you got to do the previous 49 years. You can't just skip to year 50 using this iterative concept. I'm not saying there isn't a way to just go straight to year 50. There is. That's the ultimate point of this section and chapter. But what we need to do is actually develop a formula for it. So this is just to go from one year to another, or from 1 month to another, or from one day to another. So if I say your bank account is compounding interest monthly, that means if you wanted to find January of 2021, you'd have to go through year 2020, January, February, March, April, May, June, July, August, September, October, November, December. That would be 12 iterations. When you compound annually, it would only take you 1 iteration. If we compounded daily, oh boy, buckle up, because you would have to do that problem 365 times just to get to the next year. And that's where you would go, oh, I'm going to use Excel. You better believe it. All right. So again, iterative method, new equals old times growth factor. Is everything with a percent of growth factor? No. You have to understand the concept. And some of you did pretty good with that idea on the previous test. Some of you were trying to do one type of percent problem and another type of percent problem. So got to get your ducks in a row. So here's what we're going to do. We're going to develop a formula that we will be able to use for compounding rates. This is when you will get growth off of the old and previous growth. So the idea of compound interest has been addressed in here very lightly previously. We saw when we had that TV loan problem, when we weren't paying it off at all, the interest for the first month was, say, $10, just throwing a random number out there. But then the interest for the second month was like $10.10. And then the interest from the third month was like $10.21. And then $10.32. That interest amount kept going up because when you take that interest and you add it onto the balance, your balance is bigger. Your interest is a product of the balance. So if your balance goes up, your interest goes up. And it causes this idea of compounding. You're getting money on money. It's when you get growth off of the old and the interest. Interest being previous growth. So we're going to develop a formula to be able to go straight from year 0 to year 50 or to year 1,000 or to year 2, whatever we want, without doing all the middlemen and women. So I'm giving a big hint for this. After each time interval, the new old will be the previous new. This idea we've already addressed in Excel. I circled one less word than I meant to. The new old will be the old new. And in other words, when you find your balance at the end of year one, say it's $10,000, 200. That's your starting balance for year two. And then, sorry, I got something in my throat. Whew. Oh, that was bad. I'm glad I muted for that one. Okay. Where was I? I've lost my train of thought. The new old is the old new. So your beginning balance of year two becomes an ending balance of year two after you get your interest. Then that ending balance of year two becomes the beginning balance of year three. Then you gain interest, and that becomes the ending balance of year three. And then that value becomes the starting balance of year four. So the new old will be the old new, and we're going to end up chaining some things together to condense this formula if we're doing it right. So let's talk about, and these are just some letters we're going to see later. Give ourselves some good space. Let's go to year zero. Year zero, before we gain any money, we've just got some old amount. I'm using generic words. And if you wanted to give that a letter like P later, we will. So that's the old amount. That's the original amount. It's just another way of saying original. That's our $10,000 deposit that I keep talking about. So you can call it old or original. Then in year one, I am so sorry, everyone. All right, year one, well, at the end of it, at the end of year one, so that's what I'm talking about for each of these, we'll have the new amount. And that new amount is the old amount times the growth factor, which is the old amount times 1 plus r. Our growth factor, we're growing money. We're usually growing in this course. It is rare that we're decaying. We will see a couple problems. If it was decaying, it would be 1 minus r. That's the only difference. Our money is growing. So this is the new amount. It's the old times 1 plus r, or the original times 1 plus r. Okay, so let's just hold on to that, and now let's go year two. The new amount in year two, now this is not the same. These are not the same. I'm talking about the new amount in year two. The new amount in year two is not the new amount in year one. So this is the previous amount. I'm not trying to say old or original here. I'm trying to say the previous amount from the previous year. It's not necessarily the original value. And in fact, when I say old, I do want to erase that and call it original. It's a little more sensible that way. Because if I say old, you might be thinking in year 5, I'm talking about the old of year 4. Okay, so the new amount should be the previous amount times the growth factor, which is 1 plus r. But here's the thing. The previous, oh, why is it so bad today? The previous amount, this is like us linking that Excel, it's the ending amount from year 1. In year 2, the previous amount means the ending amount from year. So those two things are the same. So I'm supposed to write, and I'm going to write it in blue to show you the change. It's the original amount times 1 plus r. Again, this right here was this right here, which is this right here. But that's not the whole thing. There was also this 1 plus r next to it. So again, in blue, this was the highlighted section. The previous amount, which was the original amount times the growth factor. So now in year 2, we still have that original amount in the problem. That's kind of cool. It's still going to harken back to our 10,000, but look at this. There's an extra 1 plus r. There's 2 of these bad boys. So if you have 5 times 5, that's 5 squared. If you have x times x, that's x squared. So we could compress this. You will need to chain some things together. Compress, chain, that's what I'm talking about. As the original times 1 plus r to the second power. 5 times 5 is 5 squared. X times x is x squared. So 1 plus r times 1 plus r is 1 plus r squared. So that says that the new amount in year 2 can be calculated as whatever you have as your original amount times the growth factor squared. Now let's go to year 3. The new amount for year 3 should be the previous ending amount times another growth factor. Now, when I say previous amount, that's the ending value from the previous year. So look at this. This original times 1 plus r squared, I'll write that in red since I have it red underlined. So the previous amount here, I'm going to write what I have here. Instead of writing previous, I write original times 1 plus r squared. So original times 1 plus r squared. But we still have this extra 1 plus r that needs to go here. Are you starting to see the pattern? So 1 plus r squared times 1 plus r, you can condense that, you can compress it, you can chain it together. It's just the original times 1 plus r to the, all right, what's 5 squared times 5? It's 5 cubed. What's x squared times x? It's x cubed. That's 1 plus r cubed. And you could do this year 4, year 5, year 6, year 7, however long you need to do this. We'll do it one more just to make sure we've got this hammered in. The new amount for year 4 should be the previous amount times an extra 1 plus r. We get an extra 1 plus r each year. We get an extra growth factor each year. But this previous amount should be the ending amount from year 3. So in blue, I'll write original times 1 plus r to the third. But we have the extra growth factor, giving us the original times 1 plus r to the fourth. So year 5 ends up being original times 1 plus r to the fifth. Year 6 ends up being original times 1 plus r to the sixth. Year 20 ends up being original times 1 plus r to the 20. Let's generalize this and say year t. See, we kind of did a process like this on that test, if you remember. The new, and let's just go straight to this. All right, so for year 4, the exponent was a 4. For year 2, the exponent was a 2. For year 1, the exponent's a 1. So if we have year t, this should just be the original amount times 1 plus r to the t. And there it is. So this just says any new amount can be found to be the product of the original amount times the growth factor raised to however long you're looking into it. So if you're looking 50 years in, then your exponent's a 50. That looks like a terrible exponent. Let me make that a little prettier. There we go. This is the concept of exponential growth. Its picture is not a line, it bends. And I will show you what that bending looks like in just a minute. So this, what this will do for us is allow us to find for any year t without the iterative process. So if you want to know year 50, you go straight to year 50. If you want to know year 2000, you go straight to year 2000. you want to know year 5, you don't need years 1, 2, 3, and 4 to find out year 5. Now, both concepts are equally important. We definitely need the iterative version of things because a lot of people want tables of information and to see how everything has changed over time. But then there's a lot of people that just want to know what's the ending value, what am I going to have at the end? And they don't need the middleman. So, lines. We know what a line looks like. A linear model looks something like this. It doesn't have to necessarily start at that height. It can start at the origin, it can start below it, but that's a linear model. An exponential growth model ends up looking something like this. It usually has some starting value. It could, you might think it can start at 0, but it actually can't unless it has a shifting factor, which we won't be applying in this course. So it has some starting value still. But what happens is, it starts out pretty slow at first, and then at some point, roughly around here, it starts growing faster and faster until at some point way up here, it eventually explodes. So in the fast zone, I like to say that it explodes. Exponential explosion, you can see why I like that word. Because this thing just picks up pace insanely fast. Now, at what point of time, how many years in, that's highly variable depending on your growth rate, your compounding intervals, your starting value. It's definitely going to depend on the context of the problem. Sometimes we can see this explosion of money in maybe 10 years with a high growth rate. Sometimes we might see the explosion happen in like 40 years because we've got a very slow rate, or maybe 100 years because it's a ridiculously low rate, like a savings account at a brick and mortar bank, earning 0.1% interest. Ugh, terrible. All right, so this idea of NEV, I said erase, please erase, thank you. The new amount is the old times the growth factor raised to an exponent, that's your time. So what we're gonna do is we're going to take that thing, which was new equals original times 1 plus r to the t, and we're just gonna give it less, what? There we go. We're gonna give it some more common letters, and please note, these are not the only letters you'll see in this course. So A, the future value, that's what we call the new. P, the principal, that's what we call the original. R, the annual interest rate, there's no surprise there. T, the time in years, there's no surprise there. So when we compound annually, when we gain money once per year, or whatever it is we're gaining, it's not always just money. Maybe we're talking about gaining cells over a year or something like that, which is not a great model, but you certainly could make it. All right, so compounding annually, A, which is the future value, that's the new, equals P, the principal, which we said is the original, times 1 plus R, that's your growth factor, and then raised to the amount of time in years. And please note that this is for compounding annually only. I would prefer that you memorize this formula. Whether or not I'm going to put it on a formula sheet, which I'm not saying yet. For now, I'm going to say you need to memorize this formula. Maybe I don't make you memorize it, maybe I do. So here's the thing. For these next several chapters and sections, we're going to be giving you a bunch of formulas, and they kind of start from here and they just get worse and worse and worse. Now, the worse and worse and worse ones, I will give those to you on a formula sheet. I will put it in Canvas very soon, over the next couple of days, if not the next week. And all I'm saying is maybe I put the compounding annually up there, maybe I don't. And I'll even admit, I change this from semester to semester. Some semesters I make my students memorize this one, some I don't. And I have a reason for that, and it's because this is the base level of exponential growth, so I feel like it should be memorized. However, you can also figure this out based on some of the formulas of the formula sheet if you just kind of trim the fat on 1 or 2 of them. And I'll even tell you how to do that, in fact. All right, so that's for compounding annually only. I'm going to give you a hint as to what we'll be talking about some next time. What if we were to compound on a shorter interval like months or quarters or days? What change happens to this formula? Because two of these things are going to change. Maybe it's the P, maybe it's the R, maybe it's the T. Two of those three things will change.
All right, just had to get the next video portion up. And obviously you can see we're going into the guided activity section for 6.1. So here we go. All
right, so I'm going to really quickly talk about this guided activity on page 224, the one that I said might be our activity, but I'm actually going to make y'all do the one on page 226 because there's different rates, and I'm gonna kind of give you a way to go through these. All right. So guided activity 1, compound interest. You invest $1,000 into a mutual fund. What's a mutual fund? A mutual fund is basically a bundle of stocks or bonds or mortgage-backed securities, basically just stocks and bonds pretty much, but they can be other things. It's instead of just buying Apple, or instead of just buying Tesla, or instead of just buying Amazon, you have a mutual fund that has a whole bundle of these. So you get to buy Apple and Amazon and Tesla and maybe 20 or 30 or 500 other stocks as well. We'll talk about that more in chapter 8, but let's just think about it as a fancy type of savings account. Now, in the real world, these fancy savings accounts do not always return the same number each year. However, you can calculate over 30 or 40 years an average. So maybe this fund, if you actually looked at it 30, 40 years, it just averaged out to be 9% per year. So that's the number we're going to use. Savings accounts are pretty static in numbers, but stocks, bonds, mutual funds, they vary literally every day. So we start out with $1,000. They ask us, how much do we get in interest and how much do we have at the end? Now remember, for this very simple concept, whenever we look at the smallest interval possible, interest is just a product of the balance and the periodic rate. Now, we're getting a return of 9% each year, so that's an annual rate or an APR. So our period is assumed to be annual. If I said that it compounded monthly or something like that, which we'll get into later today, then this interest would be calculating every month, but we're calculating the interest every year. So all we got to do is pull out our calculator like I always forget to do on this screen, then pull up the annotate. Boom, there we go. So to find the interest, we're just taking the $1,000, ignore that trigonometry, $1,000 times the 9%. Now, if you do this in Excel, it can calculate that 9% for you by just using 9%. But in our calculator here, we got to do a decimal, so times 0.09, and that will give us $90. So that will be what goes here in the interest. And then the ending balance, the new balance, is always the sum of the previous balance and the interest. So the new balance is the old plus the interest. Now you might say, hold on, Mr. Beckner, you said the new balance is the old times the growth factor. Yes, both are true. That's two different approaches. What we've done is a two-step process here. We found the interest, then the ending balance. If you wanted to use the other version, new equals old times 1 plus r, check this out. If we do 1,000, then parentheses, your calculator, you might have to hit times first, and then the 1 plus the rate as a as a decimal, so 0.09. And look at that, we get 1,090, which is exactly what 1,000 plus $90 is. If you took the 1,000, which was the starting balance, and you added the interest, which was the 90, you would still get 1090. It's two different ways to get the same answer. So why would we have two different ways? Because sometimes we want to know the interest along the way. Sometimes we're only interested, pun unintended, in the ending balance. We don't want to know the interest. So if all we were worried about is start and end, start and end, start and end, I could just use this over and over and over. But if we're actually curious, well, how much money did we get for free along the way, which is what I like to call interest, free money, then you can do it in this two-step process. All right, so now the new beginning balance is 1,090. The new old is the old new. Then to calculate the interest, we're going to take that 1,090 and we're going to multiply it by 0.09. And we get $98.10. And clearly, I say clearly, but sorry, I can't hit my mute button when this annotate menu is up, unfortunately. If you add these two, 1090 and 9810, you're going to get $1,188.10. The same as if you instead just took your previous balance, the old, times the growth factor 1 plus 0.09. You still get that 1188.10. And that's this entire process. I'm not going to do this for all 10 of these rows. Originally for the homework, I was going to say, let's just have y'all complete these. But I'm going to do things a little differently, in fact. I'm going to get y'all a little more involved. Okay, so then the new balance from year 2 will be the original balance from year 3, so 1188.10. And then from there, you can go off of annotate. You can take the 1188.10 cents times the 0.09 to get your interest. So that would be $106 right here. And then you can add that to the 1188.10 to get the new balance, which is $12.95. And we're going to round to the nearest penny, so 0.93 and 0.03 for those problems. So let's go back and annotate. Write this last one. 106.93, and then for an ending balance of 1295.03. Sorry if that 5 looks a little ugly, but you can see it on the calculator. All right, now if you keep going with this, I want to point out just a couple more answers. The ending balance for year 8 ends up being 1992.56. The ending balance for year 9 is 2171.89. And the only reason I'm doing that is because they ask about how many years does it take to double your money? And how many years does it take to double your money? I think there are two legitimate answers here. Most people would say 8 years because 1992 is extremely close to 2000, which we put in 1,000, so doubling would be 2,000. So 8 years would be one student's answer. However, in the real world, let's say you actually had to exactly double your money to pay something. In 8 years, you don't have that $2,000. You're $7 and I can't even see the cents anymore, but it doesn't matter. You're about $7 or $8 short. And that store is going to say, no, sir, you can't buy it unless you give me that other $7 or $8, or no, ma'am, or whatever. So in the real world, you technically never doubled your money until 9 years. However, most people would say 8 because it's extremely close. So then they ask, is your ending balance each year a linear function of the years? Why or why not? So if it was linear, that means that every year it would be going up the same amount. So every time we add 1 year here, we would, okay, so we added $90 here. So we would expect this to add 90 and then add 90 and then add 90, etc. Because we gained $90 in interest first. But unfortunately, those are all wrong. Our interest got bigger and bigger and bigger and bigger and bigger that you can't see. I will use Excel later, sooner than later, in fact, to really address that because this takes forever by hand for obvious reasons. So no, this is not linear. This is that exponential growth. Constant percent change. We are constantly changing at the same percent every year. We're gaining 9% more every year. But because every year we have more, 9% of more is more, and then you get even more, and 9% of even more is even more. And I know that might sound silly, but it's true. And then the last question they ask, which you can't see on the screen, but number 4 is to write a model or an equation for after 10 years. And then what this relates to is that equation I gave you last time, that A is equal to P parentheses 1 plus R raised to the T. That was the formula we developed so that we didn't have to go year by year by year by year by year. I could just go to straight to year 10. So the principal is the starting value, which is 1,000. So you go A equals 1,000, then times 1 plus the rate of 9% is still 1 plus 0.09 raised to the T. Well, that's in, you can't see it, but I did say 10 years. So the exponent would be a 10. That's it. You could even simplify this to 1,000 times, I won't need a parentheses because 1 plus 0.09 is 1.09, then raised to the 10th. You would not multiply first. PEMDAS is still important in your calculator. It would do this first. So if you're doing it step by step, you would have to do that same thing. And then you'd multiply by the 1,000. So if you want to know what happens at the end of year 10, you can just go 1,000 times 1.09 raised to the 10th power. And we can see that we would have $2,367.36 at the end of year 10. That would be our remaining balance. Now, maybe you don't trust this formula. Well, we did show it iteratively for years 1, 2, and 3. So let's see if we can confirm year 3's amount. So that just means change the exponent to a 3. So 1,000 times 1.09 raised to the 3rd power. And we get 1295.03. Look at that, 1295.03. So this formula does, in fact, work. And again, there are times when you want to know all these middle years, 4, 5, 6, 7, 8, 9, 10. There are times when you're only interested in the last year. It depends on what you want for your in finance stuff. If you're being hired to do something like this, it depends on if your customer wants a spreadsheet of all 40 or 50 years of growth, or if they just want to know the ending balance. So there's a lot of dependability. And for us in this course, it just depends on what the question asks, right? That's what matters. All right, so let's clear our screen. Try and just hold a picture of these numbers in your head, or hopefully you wrote them down somewhere, because I will refer back to them later, especially the year 9 and 10, 2171.89, and then the 1295.03. I'm sorry, 2367.36. All right, I gotta clear my screen. Take off of annotate. So let's take this and let's do it in Excel instead. So we're going to take this problem. I'm going to open Excel. And this is going to be, that was the answers and stuff to later. Luckily, you didn't see too much of it. And I'm going to try and make a spreadsheet that just kind of mimics this. I'm going to zoom in a little because I won't need that much space. So let's have column 1 be the year, column 2 be the starting balance, column 3 be the interest, and then the ending balance. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, I can just type 1, fill down by holding control, or type 1 and 2, grab both, fill down from there, but it's only 10 years, so that's not too bad. We started with $1,000. The interest is going to be the product of the balance and the interest rate, which is 9%. Now, I could put the interest rate somewhere else if I really wanted to, and then do a fixed cell reference. But for this problem, I won't. I'll do that later, though. So I can just go equals the balance, which is in this cell, B2, times the interest rate, which we said is 9%. Now, in Excel, I don't have to write that as 0.09. I can actually just type 9%. And look at that, we get $90. The ending balance should be the sum of the start and the interest, so we go equals. And I don't need to write sum in parentheses since it's just two things, just click, plus, click. Easy as pie. There we go. Now I can't just drag all of these down from here. If I do this, those are clearly not the right answers. So what did we do wrong? Remember, with all these finance problems, before we can start filling things down, year two's starting balance must be linked to year one's ending balance. We have to make sure these two things are exactly the same. And if I just try and do this, clearly they're not. So we go to this cell. This is a super important thing, and I know I haven't done it in class in a while, so this is your friendly reminder. We'll see it a couple times today. Equals, just click the cell with the previous ending balance, and they're linked. There we go. Now we can drag the interest formula down, grab the fill bar, and that answer is exactly what we saw before, except it doesn't look like it because it's not showing enough decimal accuracy. We'll fix that in a second. The ending balance, if I drag it down, again, minus the change, it's correct. So let's just highlight all these cells and let's change their decimal precision to 2 decimal places so we see money. And now we can see that it's $98.10. All right. Now I don't have to do this manual linking anymore because that was already done one above. See, if I double click, we can see that it's linked. So if I grab that cell, grab its fill handle, drag it down, if I double click it, you can see that it's linked to the previous balance. So I can just fill all these down now. I can fill all these interest down. It looks wrong for now, but hold your horses. Still looks wrong, but now it'll look right. And that answer, 2367.36, is exactly what I said year 10 would be based on the formula. You can see the year 2 and year 3 amounts are exactly what we calculated. The year 9 amount I foreshadowed for you. I didn't show the calculation, but I did tell you it at least, as well as year 8. So now we can tell that in 8 years, we pretty much doubled our money, but we didn't officially double it until 9 years. And yeah, there we go. Now, what if I wanted to see this for 50 years? Well, I can just grab all these cells now, drag it down. Now you might think, oh, we'll just go until you're on row 50, but that's not quite right. You have to go to 51 because the first row was labels. So year 1 was actually in row 2, which means year 50 is in row 51. Uh-oh, Mr. Beckner, you broke Excel. No, I didn't. It's just these numbers are too big to fit in there. Sometimes zooming out will get them there, but not quite there. If that doesn't work, you can just widen your cells, and that's going to fix everything. Just widen your cells. Remember, grab the bar between the letters. You can't just grab down here. It has to be between the letters. That's a critical issue. So 50 years in, we got 74 grand. Holy cow. That's pretty great. So again, this was the actual problem. I just showed you extending the concept, and we'll go a little further into that with the problems I made up that we'll do soon. All right, so what is your homework to do? Page 226. We're going to be working with this table. Now, I'm going to need every single student to do one of each column. So it's just per usual where you come in, if nobody's done any, that means that you'll do year 1. If when you come in, someone has done year 6, that means you're going to calculate year 7. We're not necessarily going to stop at year 10 because we have more than 10 students in the course. So if you come in and someone's done a 10th, you don't go, oh, I don't have one to do. Yes, you do. Just do year 11. And then the next student can do year 12. And the next student can do year 49,000 if I had 49,000 students. So all we are doing is finding the ending amounts for this table. We're not calculating the interest. We're just calculating the ending amounts. So the ending amounts only. So if you look back at the previous problem, that was the 1,090 for the end of year 1. That was the $1,188.10 for the end of year 2. So each student has to do 4 of them, one of them based on a 5% rate, one of them based on a 12.8% rate, one of them based on a -6% rate, and then one of them based on a 20% rate. Now, please note, one of them is negative. This means you're losing money each year. This means that your money is going to go from $1,000 to, I don't know, maybe $900 and some change, and then down to $800 and some change, and then eventually $700 some change, eventually $600 and some change. So this one will be going down. So that's not a growth factor. It's a decay factor. It's the 1 minus r instead. I'm going to go ahead and give you these factors. For the 5%, that's 1 plus 0.05, which is 1.05. Remember, a growth or decay factor is 1 plus or minus the r as a decimal. So that's 0.05. 0.128, negative 0.06, and 0.20. So 1 plus the 0.128, sorry if that's a little squished, is 1.128. If you're doing 1 minus 0.06, that's actually 0.94. So growth is always 1 and then a decimal. Decay, it means it's going to be less than 1 because we're losing money. So multiplying by a number less than 1 is what causes the loss. And then with 1 plus 0.20, that's 1.20 or just 1.2. And then what formula are you using for each of these? It's new equals old times either growth factor or decay factor, whichever is relevant. So it's growth for the first, second, and fourth. It's decay for the third. So again, each student, student 1 will do year 1. Student 2, I don't know why I was about to use Roman numerals. Student 2 will go in and do year 2, excuse me. Student 3 will do year 3. You get the idea. This discussion board should be live before 1:30 today. So again, if I have 15 students that do this, then that means I should have 15 years completed in the end. I will come in, and if I see anything wildly incorrect, I will correct at that point. I won't worry about people going back and correcting previous ones. I might say that one person that I corrected can correct it, but I don't want to have to go back and make everybody correct it, especially since you're doing 4. So this is not a lot of work. It's really just 4 answers for each student. Every student must answer it. If you don't answer one, you'll get a 0 for this discussion board. And like we said, this will be due on Monday, the 23rd. So again, that's Monday, the 23rd by midnight. Shouldn't be too bad. I defer you to the previous example that I was doing with y'all. If you don't know what to do, remember, YouTube has the recording, so there are no excuses. You don't have to find the interest and then the ending balance. Yes, you could, but I would prefer you do it just going straight from the old to the new. Please talk about your work. Do not just say the answers. Just saying the answers is not a discussion board. So write out your formula, write the answer. You could even say if it made sense or not. And what I would really like you to do is just to notice how these numbers are going to have a large effect. The 5% is going to be kind of a medium-paced growth. 12.8% is going to be a pretty solid growth. 20% is going to be insane growth. I'll even point out the year 10 answers in approximation, just so we can tell if we're on a good path. Year 10 is about 1,600. Again, about, I'm not saying that's close by 1 or 2, it's just within 100 or something. This is about 3,300. This is going to be about 500, and then this one's going to be about 6,100. 6,100, so 20% growth 10 years in, you've sextupled your starting amount of $1,000. That's insane. 5%, you've only gained 60% of it. 12.8%, we've about tripled it. Negative 6%, woo, looks like we've been investing in oil too much. Shots fired. All right, so that's your group work, your discussion board, so to say. Remember, any questions, email. You can ask questions in the discussion board if you like. Oops, I forgot to clear the screen. Always forget to do that. And that should be it for that. Okay, so now we're going to go off the cuff. As a reminder, I just reminded you of this formula a bit ago. If you want to go straight to an ending year, this is your formula that I said you may or may not have to memorize. I haven't even told you if you have to memorize it yet because I'd like you to memorize it. Even if I put it on a formula sheet for your final exam, I would like you to memorize this formula. It's not a complicated formula. It's just new or the newest equals the oldest times a growth factor raised to an exponent. The only thing that's different in this versus new equals old times growth factor is the exponent, and that takes you from oldest to newest without the middleman. It's a pretty simple formula. Now, I'm not even going to be doing anything with this formula for a bit, but I'm just going to remind us of that. And then we're going to go back to doing kind of what we were just doing in Excel. All right, so Bob wants to deposit 10,000. We're going to do these three examples. They're just highlighted in different colors to show the different examples. So yellow is 1, green is 2, and then the other yellow is 3. So let's just bump these off. And we're going to make some financial plans. Bob wants to deposit $10,000 into a CD for some number of years. This account accrues interest annually, so nothing new yet, at a rate of 2% per year. This was a pretty average online savings account until March of 2020 happened, and then a lot of things changed drastically. And it's just been all over the board previously. It had been as high as 4% maybe a decade or 12 years ago. It had dropped to like 0.2% for a while, and now it's kind of heading back to that. But that's because borrowing money is cheap right now, which we don't need to get into. Use this to track the amount in the account as well as his total interest for 1 year, 5 year, 10 years, and 40 years. Record these values, interest and total, and make graphs, aka a scatter chart. And when we get to the scatter chart, we want to use the years and the ending amount. And as a reminder, if you need to go over gaps in Excel, holding control will help you do that. All right, so the scatter chart stuff isn't going to be an issue for a while. So I'm specifically looking for 1, 5, 10, and 40 years in. Now I could certainly just use the formula A equals P parentheses 1 plus R raised to the T to go ahead and get those answers if I liked. I can also make Excel do that as well as get year 38, 39, 27, 21, 7, 11, whatever you like. All right, so Excel, do my bidding. Let's just make a new file. Let's close the old one. We don't want to save. All right, so we have the year, then the starting amount, then the interest, then the ending amount. And we're going to go all the way up to 40 years. So I don't want to type 1 through 40. I'm just going to type years 1 and 2, highlight both, then click the fill handle and go down to row 41. And that gives me 40 years. Wow, that was easy. The starting amount, that was the $10,000. So let's go $10,000. Then the interest, and let's format that as currency. Then the interest is going to be, let me actually just put the rate somewhere so that way I can change it. So our interest rate is going to be 2%. Just widen this column a little. So when I use that 2%, I'm not going to type equals the balance cell times 2%. I'm going to go click the balance cell times the interest rate, which I have over here. That way, if I want to change it to 5%, the entire 40 years with Excel will change with it. If I want to change it to 3%, everything changes with it. If I type the 2% here, if I wanted to change everything to 5%, it would be much more complicated. I'd have to go and change it in this cell and then fill it down all 40 years. Trust me, this is the easiest way to go, except I have an error in here. And I'll show you in a second after we move forward. So the ending balance, that's just the sum of the start and the interest. So 1 year in, we gained $200 for free, and we now have $10,200. For year 2, we just link year 1, end balance, so equals, and then click that cell. Boom. Watch what happens if I drag the interest down. It's a dash. Ooh, that's wrong. Double click the cell, and you can see why. The blue box is correct. That's the starting balance of that year, but the red box has moved down as well, so it's no longer on the 2% interest. That's because we need to fix that cell reference. We don't want that red box moving at all. So I need to delete that one, go back to the interest formula, And in the G1, let's double cache it because we don't want that red box moving. Now when I fill it down, we can see that the interest has gone up as expected. This is called compound interest. Money on free money on free money, because the free money gets added to the pile and then we get more free money on the original pile plus the free money. Drag the ending balance down, and that makes sense. Now you can, once you have row 2 completed, you can fill these down individually, or you can highlight all 3 of these and then just drag down to year 40. It is so quick. Excel is awesome for this. Let me zoom in just a little. Let me widen my columns after I do that so you can actually see your numbers. All right, so we said we wanted to track 1, 5, 10, and 40 years, so, and that was the interest and how much is in the account at the end. So the interest and how much is in the account. All right, so year 1, the interest was 200, and the ending balance is 10,200. 5, the interest was 216.49, and the ending balance, just tab this so it looks a little cleaner, was $11,040.81 for year 10. The interest was the 239.02. Pulling these out of thin air, I'm using the table. And the ending balance, ending, was year 5. I didn't do that right, did I? Yes, I did. Year 10, 12189, 94. And then for year 40, so we're just not looking at anything for a while. We made $432 for free that year and 95 cents with an ending balance of $22,080. All right, so Bob put away 10,000 bucks, and you can see how much he has. 1 year, 5 year, 10 years, 40 years in simply over here, or you can look at all 40 years over here. If you don't trust that formula we talked about, I'll at least show you your 40. We would have A, the future value, equals the starting value, not the previous value. When you use the formula to get straight to a specific year, it's the starting value times 1 plus the interest rate, which is 0.02, raised to an exponent of however many years or however much long time, if we're talking about months or days, which we'll get to later, and that'd be 40. And I can actually put that in the calculator just like that, or I can simplify the inside of the parentheses, 1 plus 0.02 being 1.02. So here's 10,000, parentheses, 1 plus 0.02, close it, raised to the 40th power. And look at this, $22,080.40 rounded to the nearest penny. If you wanted to do the 10,000 times the 1.02, if you want to go ahead and add that in your head or on paper or whatever, then do your exponent of 40, you can see you get the same answer. Doesn't matter. I actually suggest most of you do it the first way I did it, because that's less computation on your part, especially when we get to the next formula where doing that addition will be just a little more annoying because there'll be fractions involved. All right, so this works. Excel did a good job of going line by line, but also our own formula works if we're only interested in year 40 or year 10 or year 5 or year 1. Next, we said to make a scatter chart, make a graph out of this using the years and the ending amount. So we're only going to track the ending amount each year, so how much money we actually have in the account. So to do that, our years are in this far left column A, and the ending amount is in column D. Those are the only 2 things we want to highlight. I can't just drag all of it like that. We have to highlight the label and all 40 years. Then we can let go. I am now hitting and holding the control button on my, actually, hold on. I need to, that was not what I expected. Let me try that again. So I need to scroll back up though. So I haven't hit control yet. I'm gonna scroll back up. I'm holding control. Now I click ending and I highlight all 40 years worth of ending balances. See, the order I do all that is very important. I had to highlight, scroll back up, then hit control, because if you hold control and scroll, something weirder would have happened. So remember, when something weird happens in Excel, undo is your favorite friend. So those are highlighted. Let me maximize this now. Insert, scatter chart. Now I'm not having to do any recommended charts because this isn't a homework, so scatter chart right here, the top left one, and boom, there we go. This is how much we have in our account, and it says ending. You could make it a more, a better name by double clicking and just saying ending balance if you wanted to, or balance at the end of the year, whatever you want. And you can see that this is not a straight line. It kind of looks straight. It almost looks straight, but it is bending just a little bit. So I told you that exponential graphs, they tend to have this kind of shape. They tend to do something like this. They'll grow really slowly at first. They start picking up speed, and then at some point, they take off, and then they're growing just wildly. But there's a lot of factors as to how long it takes for it to explode. The two biggest factors are time and the rate. Now you might say, well, it's obvious time is a factor because that's, at some point it's going to explode. So time would be an important factor, but the rate is too. So this is not a crazy explosion. This almost looks like a line. I could do a linear approximation, in fact, and it would be pretty good. But let me clear my screen. Let's take off of annotate. Let's go back up to this interest rate. Let me hold this chart up here. Let's change the interest rate to 3%. And let's see how it affects the graph, because as soon as I do that, you'll see all these interest numbers, all these ending balance numbers, and this graph change. Look at that. We saw all these numbers change. The ending balance at year 40 is now $32,000, where originally it was $22,000. So we now have another $10,000 for free just by going from an interest rate of 2% to 3%. Also, this graph does not look nearly as linear. It's still fairly straight. It doesn't look like an explosion has happened, but it is bending a little more. Watch if I change it to 4%. It's bending a little more. Watch if I change it to, let's just jump the gun, 7%. Ah, now we're starting to see that explosion start to happen. Right around here is when we start picking up pace, and this thing is getting steeper, which means we're getting way more money for free. Now look at our ending balance of $149,000. So if you could magically find some 7% certificate of deposit, please put your money in that for 40 years. You will not be mad about it. However, CDs never go above like 4% historically. And right now, maybe 1% or 2% if you're lucky. I haven't looked at those in a while. Don't have a lot of money to put away as a teacher in the times we're in right now, especially while rebuilding a bathroom. But anyway, it's not the point of that. The point being, how do you get a 7% account? Mutual funds, retirement accounts. That's how you get your money to explode. You don't put it in a savings account. You don't put it in a checking account. You don't put it under your bed. You don't even put it in a CD. You invest in this scary, risky market because over time, 7-8% is the historical average of the top 500 companies when you buy them as a bundle. So if you do that for 40 years, and this isn't even a traditional retirement because we just put money away once. Traditional retirement, you keep adding to the pile. Mr. Beckner, how did Bob get $10,000 just to deposit randomly? Well, maybe he lost a family member and he was in the will or something like that, or maybe he got a new job and part of the new job was he got a $10,000 stipend to move or to just to actually change from one thing to another. Check this out if we change this to 12%. Now that is an explosion. You might say, well, Mr. Beckner, that doesn't look that much steeper than before. Watch the numbers though. Look at this number right here. It's almost $1 million. If I undo that, we were only up to 160,000. See this shape, it doesn't look like it's changed that drastically, but that's because the scale of the window has changed dramatically. Before our window, we were only like down here. Before, this was all we were looking at, just this window. Now we've gone way past it. We have just made an insane amount of money if we can find some retirement fund that earns 12% interest, and now we got $930,000 off of just putting $10,000 away for a very long time. Again, this is not how most of us are going to do anything in the world. 99 out of 100 of us are not just going to put 10 grand away and not add to it or just hope that's a retirement plan. We got to keep adding that pile over and over and over. All right, back to finance problems. Let's do the second one. So now Bob has, so we saw that the initial problem of 2% interest rate, we gained about $12,000 for free. By the way, I meant to mention this, the total interest is always the ending balance minus the starting balance. And I mean the actual end, the last year's end. So that would be $22,080.40 minus $10,000, which would be $12,080.40. That's what I like to call free money. Now you might be saying, well, Bob just got that $10,000 for free. You know, one of the things you said, so wouldn't it all be free? Let's not count it that way. Interest is what I mean by free money. So all those little $200 from the first year, then like $201 or $10 from the second year, all of those end up stacking up to about $12,000. But if he put that money in a higher interest account somehow, he would have got way more interest. Just look back at this one. If we end with $930,000 and we only put $10,000 in, that means we got $920,000 for free. We just got almost $1 million for free somehow. And you know what? People do this all the time. People are so terrified of retirement accounts and it just seems so confusing. Yes, it can be. You can make it extremely complicated, but you can also make it simple by buying one index fund for all of your life, something like the S&P 500, the top 500 companies of our country, and then just ride that for 40 years. And while you're going to have bad years, you're going to have some amazing years that'll make up for it. And in the end, you'll make lots of money as long as things continue like they always have. Speculation, this is not financial advice. This is just for educational purposes, so you cannot sue me. Please and thank you. All right, now back to the new problem. How are we on time? We got time. Bob has $30,000 that he received from his grandma. Very nice grandma, or maybe this is the sad story. I don't know, but Bob got $30,000. Maybe Granny got $3 billion investing, and she's just giving away 30 grand like it's nothing. He's going to deposit it into a mutual fund. So this is that retirement scenario I've mentioned, earning 8%. And they don't have to be used for retirement. You can invest in mutual funds and not use it for retirement. Just use it to buy a house 5 years from now or get a deposit on a car, something like that. But I tend to address them as a retirement account. So 8% is, again, average long-term. It's not like you're going to get 8% this year, 8% next year. You might get 30% this year. You might lose 40% next year and then gain 100% the year after that. It's a wild ride. Buckle up. So he's going to deposit this money and wait 35 years. And maybe Bob's just like, well, maybe I can retire off of this. Maybe I don't have to keep adding to the pile. Maybe Bob should still be adding to the pile no matter what, because, hey, what's wrong with having more money? How much will he have? How much was free money, aka interest? Make a scatter chart as well. So I'm just going to go to Excel. I'm going to make a new sheet so I don't have to erase anything. And we're going to have our year, our starting balance, our interest, and our ending balance. And we're going to years 35. So I'll type 1 and 2, highlight both, drag them down to row 36. And if you just drag it to the wrong row, then just drag less or drag more. It's nothing complicated. We're starting with, we said, $30,000. I'm going to format that cell as currency. We said we're going to have an interest rate of 8% for our mutual fund. So our interest will go equals the balance, the current balance, times the actual interest rate. But we already know from the previous problem, oops, I forgot I have to enter, and then I have to go back and do the cash symbols, only for the reds, because the red one's the one we don't want moving. We want the blue box moving. Then the ending balance will be the sum of the start and the interest. right, that's pretty sweet. The first year we got 2,400 bucks for free, and that means that overall we now have 32,400. I cannot just highlight and fill at this point. We have to link the start of year 2 to the end of year 1. Really easy to do. We've talked about it many times now. Now we can drag the interest formula down, look for any weirdness. It went up a little, so that's good. Drag the ending balance down. That makes sense. Then we can highlight all 3 of these and just grab the fill handle and drag it down for all 35 years. I see some hashtags, so let's widen our columns until we see all the numbers. And there we go. So after 35 years, our $30,000 has, in my opinion, exploded to $443,000. Taking 10,000 and turning it into 20,000 over 30 years or 40 years is not an explosion. Taking 30 grand and multiplying it by more than a factor of 10 over the life of you working, that's an explosion. That's a holy cow, we just made a lot of money for free. Now you might be going, well, Mr. Beckner, I got to pay taxes on this. Yeah, okay, maybe you have to pay taxes depending on how you invested. Boo-hoo. Again, you just got over $400,000 for free. Uncle Sam might take 25% of that. At least you still got 300 grand for free. You are not going to be sad over that because person B, who didn't put their money in the market, who's not paying the taxes on $400,000 worth of interest, doesn't get anything. So boo-hoo, pay your taxes. Account for them as well. Now, notice I said something about maybe there's a way you can avoid paying taxes on this. Dropping $30,000 all at once, you're going to have a hard time avoiding that. But if you're doing like $6,000 a year into an IRA, you can get all that interest for free, specifically a Roth IRA where all of your interest is free, tax-free that is. And that means you just earned, maybe $500,000, $1 million in free money that you don't even get taxed. Roth IRAs, if you're young, get yourself a Roth IRA. Start it tomorrow if you're employed. If you're not employed, you can't do an IRA yet. You gotta have a job. But yeah, all right, so let's make our chart. So highlight all the years. Let go. Scroll back up. Before I hit anything else, I'm gonna hit and hold Control, highlight the ending balance. Let go. Then insert, scatter chart, boom. Look at that, it's got a nice bend to it. That's our explosion. You can even insert a trend into this. So remember, we go to add chart element, trend line. If you do a linear, look at how bad of an approximation that is. That's really not good at all. Oh, but look at the one that says underneath it, exponential. Wow, I can barely even see the model. Look at how the dots, the bigger dots, now they're going to have little dots between them. That's because this is an exact exponential model. We're not doing any subtle little changes like, oh, we got 9% this year and then 8% the next year. None of that goofy business. We're keeping everything the same, which means this model is a 100% accurate fit. If I were to display the equation, it would be perfect. And I can do that. Add chart element, trend line, more options. Why did the line pop up? Did I hit something on accident? Okay. That's the wrong menu, so I close it and try it again. Trend line, more options. It's just weird how Excel does that sometimes. Oh, I see why. Why is it doing that? I have literally never seen Excel do that to me. Go back to exponential, you silly goose. Display equation. So there's our equation. Don't worry about that what little e means yet. We'll talk about that in 6.2. And then if you display the r squared, I said if this number is a 1, it's perfect. And look at that, it's perfect. We'll talk about the r squared in chapter 8. We'll talk about that e in the next section. So that's a perfect model. All right, so 8%, that's pretty much average. Maybe you actually learn a bit about investing. Maybe you learn how to beat the average in theory by picking tech and medical companies right now, or maybe something else 10 years from now, and maybe you're able to get yourself a 12% interest rate over the average of 35 years. So the ending amount, which was like 440,000, holy freaking cow, I got to widen the column again because it got into $1.6 million. Woo, buddy, that's a lot of money. All right, but let's take it back to the 8%. I also asked what the free money was, the interest. So that's just the difference of the final amount and the starting amount. So we're just going to take 443,000, blah, 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 minus 30,000, which would be 413,560 and 33 cents. So that, I just need to move that over there. The free money is the total interest, which is the 443,560.33 minus what we put in, which is 30,000. I should have dollar symbols everywhere, but just go with it for now. 413,560,33. That's the free money we got. Pretty nice for just putting $30,000 away and not touching it for 35 years. Why am I doing this? Because sometimes people inherit a good chunk of money, 20, 30,000. It sounds like a whole lot, especially when you're 20 or 30, maybe even 40, maybe when you're 50. So it just depends on your life. Still sounds like a lot of money to me. But what a lot of people do with those inherited dollars is they go buy a brand new Jeep, or they spend it on something just super frivolous. And I'm not saying don't spend any money frivolously on yourself. Again, live your life to your style, but just understand that you're paying a bigger price tag than you think, because that $30,000 you used to go buy a brand new Jeep, if you instead had just stuck with the car you had, if it was fine, or maybe buy like a used car for maybe a third of that amount, you could take that 20 grand, put it away, and have hundreds of thousands of dollars later. So everything you buy today has a price on it of what you could have had 20, 30, 40 years from now by not buying it today. It's called opportunity cost. That Starbucks cup of coffee, if you're 18 and buying $4 for a latte every single day, that's costing you $1 million in the long run. Now, it's only actually 60 grand out of your pocket, or 70 grand, somewhere in that ballpark. But when you consider if you had taken that money and invested it over 30, 40, 50 years, it turns into $1 million. And I'll show that. Not right now, but I will. Actually, that was a lie. I will right now. I was thinking I had a different problem before this one, but there we go. Do I have enough time to do this one? I think I have just enough time. So Bob is 18 and wants to retire at 68. Instead of buying a Starbucks beverage at an average of $3.50 a day, so he's not even getting the fanciest beverage there. He's not even getting a biscuit or a pastry to go with it. Now, what he's going to do is deposit his annual savings into a 9% mutual fund. So again, just a tick better than the average. How much will Bob retire on? How much was free money? Make your scatter chart, make an analysis, think about if that Starbucks coffee is still worth it. Then ultimately, what if Bob starts at 28? What if Bob starts at 38? What is the effect of waiting 10 years? Because so many of us go, nah, I don't need to start doing this now. If I wait 10 years, it's not going to have that much of an effect on me. Oh boy, are you wrong. Every 10 years is a significant effect in how much money you need to be putting away to get that same goal. All right, so let's get it. All right, new page. Now, this one is going to look a little different in a couple of ways. Let's go year, starting amount. We're no longer just putting money in and leaving it there. We're adding to the pile. So I need a column for money added each year. So I did not need to hit enter. That's okay. Then I'm going to have a column for how much we have before we get interest. Then I'm going to have a column for how much we actually get for the interest, and then for the ending balance. And we're going to do this for 50 years because he's 18 and he's going to 68. Retirement age, Social Security, full Social Security right now is 67. A lot of people's pensions and retirement plans, they say you're going to 67, maybe 62. Just depends on where you are in your life. So let's do this for 50 years. So I got to go to row 51. Boom, there's 50 years. Now, again, I have this money added and a pre-interest balance in here, which looks a little different. And that's because, again, we are starting with nothing. We start with nothing. We have no money at first. This formula is currency. That dash means zero. Don't worry about that. You can still see the zero is typed there. Now, how much money do we actually add the first year? Oh, we add $3.50. No, that is completely wrong. That doesn't make sense. We bought a Starbucks coffee every single day. Now, you probably didn't get it certain days, but let's just assume we did. Maybe you were buying a little bit more some days, and then it just averages out to $3.50 a day. So no, it's $3.50 a day for 365 days. So that $3.50 per day, we're going to do that for 365 days. Look at how much your Starbucks habit is costing you a year. $1,277.50. It doesn't sound so bad when you're buying it $3.50 at a time, but if you do it every day, that's $1,000. This is one of the points that I'm trying to make everyone kind of understand with your monthly budget. If any of us do have just regular expenses that we don't necessarily need to do, when we could go to the grocery store and get coffee for like 20 cents a cup. Now, again, I'm not telling you how to run your life. I'm just making you aware of options. So we're adding this money annually. We're not going to put it in every day. Now, in the real world, it's better for you to do it like every day or every week or every month. But for keeping this problem simple, because we haven't gotten into the crazier ones yet, let's just keep it at putting the money in all at once, that $12,750. And that's a currency as well. Now, pre-interest, before we get any interest, because we're putting this in the end of the, or let's say we put this at the beginning of the year. There is two different ways of doing this problem, whether you put the 12,750 at the first day of the year or the last day of the year. Let's assume we did it the first day of the year. So there's a year zero in theory where we built up our first $1,277.50 to deposit. So year zero, we built that $3.50 up for a year. Then on January 1st of year one, we deposit the 12,750. So before we gain our interest, this is going to be a sum because we have to take what we had in the account at the beginning of the year plus what we added in at also the very beginning of the year. So this will go equals, you take your starting balance and you add what you added in over the year, or January 1 actually. Interest is still just balance times an interest rate, but I don't have the interest rate written anywhere, so let's go rate, which we said was 9%. So we'll go equals the pre-interest balance. See, it's not the starting amount. It's not what we added. It's the sum of what we had at the beginning of the year plus what we added at the beginning of the year. So that's why I have this pre-interest balance times the interest rate, which we'll have to go back and fix. And by fix, I mean double cash. Oh, okay, 114 bucks for free, 115 bucks for free when rounded. Not bad. How about the ending balance? Well, that's the sum of what we had before interest and what we had after. So equals this one plus this one. So now we got almost 1,400 bucks. Oh, well, whoop-de-doo. Now you might see this little green thing right here. That's Excel saying, is that exactly what you meant to do? And yes, it was. So you're just going to have to ignore that little green corner arrow, triangle thing. Now the starting balance is not zero. It's the ending balance. Per usual, linking the starting of year two to the ending of year one. Probably going to need to widen these columns, so let me just go ahead and do that. How much money did we add? Well, we're going to add another, from year one, we were collecting $3.50 every day. We put it under our mattress, so to speak. And then January 1st of year two, we add that exact same amount, the $12,750. Now, if I drag and drop this, if I fill it like that, it doesn't increment it by one. Sometimes it might, depending on how you're doing things. So just be careful. So if you're dragging these and it does increment it by one, just go back and change it. The pre-interest balance, well, that's going to be the sum of what we had at the beginning plus what we added. Well, that's a formula we can just drag down. So now we got almost 2,700. The interest formula we can drag down. That was incorrect, so we undo. Grab the fill handle, Mr. Beckner, and drag it down. And wow, we more than doubled our interest that year because we have more than double in the account. Ending balance, you can drag it down. Now let's see if I highlight this entire row Let me just drag it a few down. And that's exactly what I was talking about here. The money added column starts incrementing when it shouldn't. So instead, what I'll do is just do them column by column. That might fix it. It might not. We'll see. So there'll be some weirdness until all these columns are in here. Let's see if this increments it or not. It did not. And you can always hold control. That'll give you a different result. Or maybe highlight two of them and drag it. That would give you a different result. Drag the fill handle down. All right, again, nothing is going to look good until we get all of them. Honestly, at this point, I could just grab the rest, but I'm just doing it consistently. Obviously, that looks terrible because the interest got lower, but let's see what happens when we get everything completed. And I don't want to spoil the final answer. Now things are starting to make sense. The interest is going up every year. Our pre-interest balance is going up. Our ending balance is going up. Our money added, every single year, we're just putting that $3.50 away every day, which made $12,750 every year. Here's the thing, though. That Starbucks cup of coffee price is going to go up over time. So if you really wanted to be super accurate about this, you'd say, well, I'm going to inflate my deposit because the next year it's $3.70. The next year it's $3.82. The next year it's $4.01. So you'd multiply $4.01 by 365, and that would be your deposit. Maybe you just assume a constant inflation rate of 2%, which is the average. So you could actually just say each of these is 2% larger than the previous one. Because money inflates. $1 million right now is not going to be the same as $1 million 50 years from now. But holy cow, whether or not it's the same, we all know that $1 million is still a lot of money. In 50 years, we have managed to turn a bunch of lattes into $1 million. That is freaking mind-blowing, I hope. That shows you the impact of, if you are young, how just a little bit of money every single day can make you, quote, rich later. And again, this scenario is kind of a worst case scenario in my head because these deposits should be getting bigger and bigger and bigger. On top of that, when you're 40 years into your career, hopefully you're not a teacher and you're making good money. And you can go, oh, well, I've got another $5,000 to spare, so let me go ahead and add that to the pile as well. And then this $1 million might turn into $2 million. How much money did we actually put in? This is a little more unique because you can't just say we put $10,000 at the start or $30,000 at the start because we put that $3.50 in every day for 50 years. So what we need to do is just add up all the money added columns. So let me just go equals sum, open a parentheses, and then do all of the 12,750s. That was 50 years worth of Starbucks lattes, coffees, whatever. Close it, enter. We put $64,000 away. Interest is, that's going to be the difference of how much we ended with, so equals how much we ended with minus the total we deposited, which was this 64,000, and we got $1 million for free. Now, if you're employed, you can get yourself a Roth IRA, and I'll talk about this more in Chapter 9, but a Roth IRA means the money that you get for free, the interest, is tax-free. So right now, the limit on a Roth IRA is $6,000 a year. We're not even close to that. We're putting $1,200 a year away. So we've still got elbow room for tax-free growth. Lots of elbow room, in fact. So we could deposit this into a Roth IRA every single year and get $1 million tax-free. Uncle Sam would not take one penny of that $1 million if all of this had been put into a Roth IRA. Get yourself a retirement account. Get some mutual funds like the S&P 500 that are, you don't have to sit here and think about and pick your own companies. It's just, hey, the quote best 500 companies are all in one big bundle. That is a great baseline of investing. Again, this is not advice. I'm just saying, so when I say get yourself, I'm just saying what you could do. I'm not telling you what to do. And again, there are literally thousands of different mutual funds out there, if not tens of thousands. I'm just saying that most people would call the S&P 500 a baseline for comparison. There are mutual funds that do significantly better than that. There are mutual funds that do worse than it. There are mutual funds that lose over and over and over and over every year. But when you go to pick these funds, you can look at the numbers, you can look at what $10,000 is done over a decade and make a decision based on that kind of. And again, past results don't dictate future results, but it's a start at least. Don't underestimate the power of $3 a day, $4 a day. Now, maybe you're not 18, maybe you're 28. So what if Bob waited 10 years to start? Bob's like, well, you know what? I want that cup of coffee for while I'm in college and starting out my job and all this stuff. And I don't really make a lot of money. I need to worry about, my car. I need to worry about paying rent. I just can't do this, or I think I can't do this. And most of the time when you think you can't do it, you probably can, unless you're just absolutely broke and don't have income, which right now I understand that many of you might be in that situation. Again, no judgment, all in a different place. So what if you wait 10 years? That means you don't have 50 years of growth. You only have 40 years of growth from 28 to 68. So we got to cut all this out. Now we only have $470,000. But what if you still wanted to have that same amount at the end? What if you still wanted to have $1.1 million? Well, that means you're going to have to increase your deposit. So again, the answer to how much will you have to retire on was the $470,000. Is that bad? It's not bad, but it's certainly not $1 million. It's half. Starting 10 years later has lost you more than half of your retirement plan. And all it was Starbucks coffees. It wasn't like you didn't eat for a week or something, or eat for a year. So again, this was the 1.1 million. How much do you ever retire on? We already talked about that. I must have gone too far on my undos because now my interest is gone. There we go. So now let's say, all right, well, let's cut out those last 10 years, years 41 through 50. Now we only have the $470,000 to retire on. This is no longer correct because it should be cell F41. So we can see that we only put $51,000 away, but now we only got $420,000 for free. Again, that's not bad, but if you see this when you're 18, you go, ooh, let me start now because I just lost about 600 grand, almost 700 grand. How can you make that money back up though? I need to see the number, 1.13 million, okay. How can you make that money up? Well, maybe you double deposit. Maybe instead of depositing 1 cup of coffee a day, you deposit 2 cups of coffee a day. So let me just do times 2 here. Oh, that didn't work right because it's not in equals. I did that intentionally. So if I'm going to go equals, and then 2 times that, that makes me put away 2,500 every year. Now, instead of doing that formula, let me just do it as 2,500. Hold on, that wasn't right, was it? It was 2,550, 2,555. Actually, you know what? I will just drag it down. That's fine. Are all these going to be right? Yes, they are. So now we're putting 2 cups of coffee away per day. And we still haven't even met what we had before, that 1.13 million. So you think, okay, well, just change this number to, I don't know, maybe 2,700. Let's see if I fill that down. Still not enough. Maybe it needs to be about 2,900, which I'm not even saying how many cups of coffee that is. You could divide it by 365 to figure out your daily deposit. There we go, we're getting close. Maybe 3,000. That's where I'm gonna stop though. 1.1 million, close enough, so 3,000. How much is that a day? So 3,000, I'm out of time, so 3,000 divided by 365, that's $8.21 a day. So if you wait 10 years, instead of putting away $3.50 every day, you've got to put $8.22 every day. That is 130% more money. That's 230% of what you originally deposited because you waited 10 years. You have to more than double your deposit. You wait another 10 years, if you only go to year 30, if you cut this and you're trying to hit that 1.1 million, now we got to put it's probably like 6,500. and it's a little more, so maybe 6,900. I'm sorry if I'm taking an extra minute or two of your time, but I think this is important. There, let's go a nice even 7,000, maybe 7,100. I'm just trying to hit 1.1 million. 73. Oops, that's not the fill handle. I'm rushing. Slow is fast, fast is good. Close enough. 7,300. 7,300 divided by 365 is $20 a day, which in comparison to the just 1 cup of coffee a day, that is 5.7 cups of coffee a day. That is meaning you have to deposit 460% more money every day. That's 560 or 570% of the original deposit. So if you start at 18, you're putting away $3.50 a day in this 9% account. If you start at 38, you're putting 20 bucks away, which we've gone from about 1,200 a year to 7,300 a year. And right now, 7,300, you wouldn't get all of that tax-free. You could get most of it, the interest tax-free, but not all of it. So time is critical for these. All right, last final thing. Going back to the original numbers with the 50 years. There we go. Let's just highlight the years. I just want you to see the table so you can get a visual of your money exploding. Scroll back up, hit control, highlight the ending balance, all 50 years worth. We're gonna insert scatter plot. Holy freaking cow. The tightness of these dots right here is really emphasizing this explosion around year 30. Year 30, year 35, this is when our money just starts growing beyond a shadow of a doubt of we're going to make lots of money 10 years from now. It's a snowball effect. Compound interest, baby. It will take you all the way to the bank if you let it. So the next time you buy that Chick-fil-A sandwich, the next time you buy that Starbucks cup of coffee, the next time you go get your nails done or your fancy haircut or something, or you buy a really high-end car, consider your options, because that money that you're putting away towards a cup of coffee now can buy you a lot more in 50 years if you put it away properly. All right, so that's 6.1 in a nutshell. I will still talk about one or two things next class, but fortunately that won't affect the due date.
So yeah, we will still talk about one brief thing, but like I just said, it won't affect the due date. We're going to keep that as the 20th. So we'll do a teeny bit of 6.1, maybe just more than a teeny bit. And then we'll knock out 6.2. And then after that into chapter 8, and then after that into chapter 9, because these chapters are a lot briefer. We're not doing 4 sections each like chapters 1 through 5. It's generally just 2 sections each. And then chapter 9, we practically treat as one giant section. But we've already talked about all this whiteboard. So hopefully everyone is going to keep working hard, keep pushing forward. We're almost done. We're almost at that finish line. So keep working hard, get that midterm taken care of. I know most of you haven't done that yet. And please remember that the 15th, this Thursday, and then the 20th, a week from today, that next Tuesday, those classes will be straight to YouTube. You can watch them on the 15th and the 20th if you'd like, but I will have them available by the end of this evening. And then as always, if you have any questions, please email me. Besides that, take care. Again, I'm sorry about the the straight to YouTube issue, but we will be back on the 22nd. Everything will be normal and everything should be fine for the rest of the semester. All right. Have a good one, everybody.